spanned by the path starting at I. I of I is the representation spanned by path terminating at I, and S of I is simple module located, just concentrated at the vertex I. So you remember also that we defined the notion of projective and objective representations. Okay. Well, the notations are suggestive. So first of all, let us prove that the following claim, gamma, saying that P of I is projective. So actually, what does it mean? So it means that if you have a surjective map, M to N, and so these are two Q modules, and the only thing we ask for is the surjectivity of this map. And then we have our module P of I. And so let me denote this by, say, F. And we have a map from P of I to N. So say G. And we are asking whether there exists a map from P of I to M such that this triangle is commutative. So in other words, the projectivity means that surjective morphisms are mapped to surjective morphisms on the level of Hom spaces. Okay, and how to compute construct such an H? Any suggestions? So we need to construct the map H from P of I to M such that the composition of H and F is precisely G. So how can we do this?
Functor is co-represented by P of I.
Say it again, please.
We know which functor is co-represented by P of I. It's Mi and Ni.
Yes, but then so how to compute this H? How to construct it? So I mean, would be nice to have an explicit construction. So given F and H, F and G would like to see whether this H exists.
Well, G corresponds to an element in Ni, and F is vertex-wise surjective, so we can take an preimage, and it corresponds to a morphism from P of I.
Right. So the P of I, it's ith vector space attached to the ith vertex is spanned by the element EI. So recall that this EI is just an empty path starting at I and terminating at I. And so actually this E of I generates the whole module. So let us define H of EI to be just the preimage F inverse of G of EI. So here, this symbol, well, this means that we choose an arbitrary preimage of G of U. So F is surjective, therefore it does exist, but it doesn't matter what is the choice. So well, it's enough because so we can then define we have to define, since H has to be a homomorphism of modules, we have to define so H of C to be just MC applied to H of EI. So let me comment on the notations. We will need them later on. So here C is a path starting at I. So in particular, we can write it explicitly as I and alpha 1, alpha k, and then j. So this is our path. And so actually, I would better write VC. Sorry. Something is wrong with my pen. Just 1 minute. Okay, it works now. This is a vector corresponding to the path C. So PC inside P of I is a vector corresponding to C. Now, MC is by definition the composition of maps in C, in M, which are kind of prescribed by the arrows in C. So more precisely, we have M1, M alpha 2, M alpha k. So, well, this is just the composition of maps in M. So clearly, the map star is a homomorphism of modules such that the desired property holds. So G is FH. So you can see it here. Okay, so that's it. So hence PI is projective, and actually this is why it's denoted by P of I. And similarly, we have the lemma saying that I of I is injective. So meaning that if we have an injection of modules into N, and we have our I of I over here, and we have a map from M to N. So we are asking whether we can find the dashed line such that the triangle is commutative. So this does exist. So the proof is actually very similar to the proof of the projective case. I'm not going to work it out now. So, well, I might give you this as a homework, as a home problem, but we'll see. But anyway, so this is very, very similar to what we had before. Okay. So now let's go further. let's prove one more lemma about the, so maybe one remark. So assume that P1 and P2 are two projective modules. So then the direct sum is projective as well. So just for me to understand the situation, please raise your hand in Zoom if you can prove this remark. So now you can do it in Zoom.
And how to raise hands?
There is well, I forgot. So let's see. So maybe somebody, I just don't want to close the application where I write. So Andrei or Igor, can you tell how to raise the hand?
I found it in reactions.
Okay, so there are two hands raised.
If we can use some universal property of tensor product, or
but there's no tensor product here. Yes, this is a direct sum of two modules, right?
Universal property of direct sum. But okay, yeah. Maybe it's.
So what is the property? What property do you mean?
That if we have a map from F2 to A and from F2 to A, then there's a unique map from the direct sum of F1 and P1 and P2 to A.
Okay, and how would you like to use it?
So if we have a surjection from A to B and we have a map from F1 direct sum F2 to B, then if we have just we use the universal property of F2 to have a map from, because it goes through F1 and F2, so we have a map from F2 to A and from F1 to A.
Mm-hmm.
And then by the universal property, we get a map from the direct sum of F of P1 and P2 to A.
Mm-hmm. So indeed, so we have a surjection from A to B, and then we have a P1, and yeah, we have a map from P1 to B, and we know that there exists a map here. So this does exist, and we have another triangle of the similar form where we have P2 to B, and we know that does exist. And then in order to prove that P1 plus P2 is projective, we need to show that we have a map from P1 plus P2 to B, then this guy does exist also. But indeed, so we know that the existence of the map from P1 to A closed in this diagram, and from P2 to A. So we had the map from P1 plus P2. So this is somehow clear. But let's prove the opposite direction claim. Actually, it's also not that complicated, but not that obvious, saying that so if P1 plus P2 is projective, then each summand is also projective. So again, please raise your hand if you can prove this. Okay.
Maybe because we have embedding of P1 and P2 into sum, or
Yes, we do. So indeed, what we need to show is that if we have a map, surjective map of M to N, and so we have P1. We want to show that this P1 is projective. And so we have a map from P1 to N. Then we want to construct the map, which is represented by this dashed line, such that the composition, the triangle, is commutative. So how can we actually do this? So we know that P1 plus P2 is projective. So let us take this P1 plus P2. And so let me denote this by F, G. So we can consider the map here, which is given by G0, right? So it means that on P1 it's given by G, and on P2 this is just trivial map. And therefore there exists up here, say H, which commutes with well, not commutes, but such that G, comma 0 composition of H and okay. And now, so how to construct now the desired dashed map? So say H bar. So the H bar is what? So can you tell us?
restriction of H to P1.
So take H. So once again, you can see that the claim is quite simple. So the proof is quite simple. However, the claim itself is not that evident. So at least from the first glance, says that if you have a direct sum of two modules, and you know that this direct sum is projective, then you have no choice about the sum. Okay. So now, so we will see that these projective modules are rather useful, well, for many reasons. And so we've seen examples of these projective modules. But now let's somehow formulate why they are so important. Let me give you a definition. So a projective resolution of a Q module M is the exact sequence of the following form. So we have M on the right, we have P0, where all the modules are projected. So once again, projective resolution is a resolution by projective modules. Okay, and of course there is a parallel definition. So an injective resolution of a Q module M is the exact sequence of the following form. We have M instead, and then on the right we have I0, I1, IK to 0. So where all I modules are injected. Well, of course, the very existence of such a resolution is not clear, but before proving something, let us give a couple of examples. So maybe a trivial example is so let not a trivial one, but a simple one. QBAN, just the equivariant quiver on of type A on n vertices, and M be S of I. So S of I is just a one-dimensional simple representation which is located at the vertex I. So can we construct projective and injective resolutions of this M?
We should check at first, is projective or not?
Oh, is it? Let's check.
Maybe we should use P of K when K not greater than I.
Say it again, please.
Maybe we should use P of K when K less than I.
Okay, how do we use it?
So
Maybe let us first answer the question by Andrei, whether this S of I is projective or not.
So it is only if I equals n.
Andrei, do you agree?
I don't know how to check this, to be honest. It's not computational question, so I don't understand the algorithm of check.
Okay, so let us see. First of all, if I is n, do you agree that it is projective?
I don't know.
Okay, but so we've just shown, yes, that each P of I is projective, right?
Yes. Okay.
So if I is n, yes, so maybe let me write.
So then P of I is S of I, and
Absolutely.
okay.
And hence this is projective, yes? So also well, I hope that today we'll have enough time to show that any projective module is a direct sum of P of i's. So actually those P of i's are building blocks for projective modules. So any module is a direct sum, any projective module is a direct sum of P of I. And since this S of I never equals to P of I or direct sum of P of i's outside this I equals n case, then this would show that S of I is not projective in case I is not n. But of course, this can be in principle shown explicitly, so we just need to show that the property from the definition of the projectivity does not hold for S of I if I is not n. So this is kind of not too complicated. Andrei, does this make sense for you?
Okay, I understand the proposition. I don't understand the proof, but probably.
You mean the proof
Yes.
why it's not projective if I is not n, yes?
Yes, yes.
Okay, maybe why not to make this computation? So this is not so let I is not n, and we want to show that S of I is not projective. So then we need some, let's see, some map from M to N. And so we have S of I and map somewhere, which cannot be lifted. So let us take, for example, the map to, say, I of I. Okay, so this means that we have these vertices, and the S of I is supported on this vertex, yes, and I of I is this one, and that one, and this is just a map from S of I to I of I, and then we need a surjection from somewhere to I of I, and the surjection, for example, let us take here I of I plus 1. So is there a surjection from here to here?
Yes, we can just map vertices before and equal to I to like themselves, and
Yes.
the rest to 0.
Very good. So the rest is the only one, yes?
Yes, yes.
And now the question is whether there exists so this map making the diagram commutative. What do you think?
Probably it's problem with the map from ith vertex.
To where? So
We know that k located at the ith vertex should be mapped to k in like isomorphically in I plus 1.
okay, yes. So
but then we can go to the next vertex and we will come into well, we will get another isomorphism. But if we use the like direct arrow from Si to I of I, we will get 0, right?
Yeah, so let me put this. So this is I of I plus 1, yes. So we have here exactly I one-dimensional spaces, yes. And here we have S of I. And the claim is that there is no homomorphisms from S of I to I of I plus 1 at all. Yes, so because non-trivial, of course, because if we had this homomorphism, then we necessarily need this K to be mapped to this K. But you see here, this map is 0. Therefore, this square does not commute, right? So this does not exist. Okay. So therefore, S of I is not projective. So, but how to construct a projective resolution?
Well, we have a map from P of I to S of I, and its kernel is P of I plus 1.
So the projective resolution looks indeed as Dima said. So we have Si, and there's a map from P of I to S of I. Sorry. And this is a surjection, clearly. Yes, because, well, we just need all the, well, so this surjection because it is, and the kernel is E of I plus 1. Well, let me draw the picture. So this is 0 to 0 to K to 0, etc. So this is our S of I. And then here we have 0 to K to K to K. This is S of I. This is P of I, and there is a surjective map here. And the kernel is obviously P of I plus 1. Which sits inside P of I, and this is clearly an exact sequence. So you can see that the sequence is very, very short. So it has only 3 terms, and that's it. Okay, and now let's consider the injective resolution. So please raise your hand if you can construct an injective resolution of SI. Okay. Okay. Good. Andrei, any suggestions?
Okay, I can make just some guess. I don't know whether it will be.
Yeah. That's
good or
good.
bad.
Mhm.
Okay, we can try I of I as well.
Yes. So we have S of I, which sits inside I of I, yes?
Okay, but in okay, yes, we have this map. Okay,
Yes.
then the what we have we should think of co-image of
Mhm.
this, and this is I of I plus no I minus 1.
Mhm. Very good. So you see this also, this map, it also has this sequence is also rather short. It has only 3 terms and well, okay, so this is one example. Let's do another, which is kind of generalization of this one. So still Q is AN, so equi-oriented Quiver. And so let's choose 2 numbers, I and j, between 1 and n. And let U ij be an indecomposable module such that Uij k, so the kth vector space of this representation is k if, sorry for too many k's, if I k is between I and j and 0 otherwise. Okay, so this is the set, the complete set of indecomposable representations of Q. And so again, please raise your hand if you know how to construct the projective resolution of this UIG. So I see that Dima can do this, and Andrei. Igor, any suggestions?
I think that the first step is to use P of I. So
Okay.
the kernel would be P of j plus 1.
Very good. Very good. And what about injective resolution?
So E of j and E of I minus 1.
Okay, very good. So now these are our examples, so let us now formulate the following theorem, saying that for any Q module M, there exists a projective resolution the form 0 to P1 to P0 to M. So actually M here is an arbitrary representation, and the claim is so that doesn't matter what Q is. So of course better, so we don't want oriented cycles, but otherwise doesn't matter what Q is and what M is, so such a resolution does exist. So let us construct it. So the proof is very concrete. So we first construct the resolution, then prove that this is indeed a resolution. Okay. So once again, the construction is very explicit, but maybe not that pleasant. So we need some notation to formulate the result. To formulate the definitions of P0 and P1. So, well, as usual, M is represented by a collection of vector spaces, Mi. So once again, sorry for putting this I downstairs, but this is also the standard notation. I hope this never kind of makes confusion. And we have M alpha being the maps between the vertices. So here I is from Q0 and alpha from Q1. So let's define P0 as follows. So first of all, let me denote by di the dimension of Mi. So just to make the notations shorter. And so I say that P0 is a direct sum over all vertices, di times pi. So this means that we take all possible pi's, and the number of times we take pi is dictated by the dimension of Mi. So clearly this P0 is projective, since it's a direct sum of projective modules. So this is fine. And maybe the first step is to construct a map from P0 to M. And since this is going to be a resolution, maybe I denote it from the very beginning this map by G, this map by F. So we need this G, and we want G to be surjective. Okay. So we need a surjective map from P0 to M. So any suggestions how to construct it?
Maybe it's better to start from one map from P of I to M.
Right. Well, we have many P of I's in principle in P0, but each of them should be mapped somewhere. Absolutely. So how can one invent such a map?
We should point image of one vector in P of I, which is EI.
Mhm. Yes.
It can be probably arbitrary non-zero vector.
Uh-huh. Uh-huh. Good, good. And now how to somehow construct the total map from P0 to M? So
Then we complete this vector with some linear independent with it and so on.
Absolutely. So in order to somehow make the construction more kind of more concrete, or rather the notation is more concrete. So let's denote by M1 I M D I, a basis of Mi or all I from Q0. So, well, we know that the number of elements in the basis should be Gi, and it doesn't matter what basis we choose, just let's fix any. And by definition, the space P0 I contains vectors of the form EI1, EI, CI, representing empty paths in the corresponding P of. Okay. So we know that P0 is the direct sum of P of i's, and we denote the corresponding empty path vectors just by EI1, EIDI. So maybe the one question, so is it a basis of P0? So the MI's, yeah, something?
No, I think
You're right.
Yeah.
Can you comment on why?
we have also like paths of length more than 0, and they should be linearly independent with them.
Absolutely. So this is by no means the basis of P0, but these are some vectors, and we define G of Ei j, V just M I j. So once again, I sits in Q0, and G runs from 1 to D. So since Ei j generates P of generates the jth copy of P of I as Q modulo. So our formula, our rule does define the map homomorphism from P0 to M, and clearly this map is surjective. Well, since all the basis elements are covered. Okay, so the first step is over. So we have our G, which is a map from P0 to P1. From P0 to M, and this map is surjective. However, we need to control the kernel. So to this end, we need at least some elements in the kernel. So do you have any suggestions, any candidates for the elements from the kernel? So maybe just kind of an idea what are.
We can look at our Q model M as a diagram, and if we have commutative squares or some commutative cycles in our model M.
Yeah, but what do you mean by commutative cycles in M? In M, we don't have any commutativity, yes, condition.
We have some paths of operators between
We do.
Mi, and
Yes.
if one path is equal to another in M, so
What do you mean? What do you mean? One path is equal to another?
Path of operators.
So you mean you have a path and you take the composition of the operators? Yes.
Yes. Yes.
Okay. Yes.
So the corresponding paths in P0 would be in kernel.
Okay, so this does make sense, right? Actually, maybe let me also introduce some more notation. So just to write down the map explicitly, yes. So if C, which is somehow path 1 alpha k to I tilde. So if this is a path in Q, so then G of this VC J, so where this is an element in belongs to the jth copy of I, J from 1 to I. So this equals to MC of E I, right? So this just by definition, right? And indeed, Igor is saying that if the two mappings, oops, is it the right formula? So actually, so I don't like this formula. So do you?
We don't have I in left hand side or what?
Well, but as I said, this is the jth copy of PI. So if you wish,
Okay.
so there is an I, but hidden. But I still don't like the formula.
G should act on EIJ.
Say again?
G should act on EIJ.
Well, so if you want, I can put EIJ here. So this means that you have a path VCJ, yes, corresponding to the jth copy of P of I, and the trivial path EIJ is also contained in this copy. So I can put it here, but I don't like the right-hand side.
I think Igor writes that G should act on EIJ.
No, but you see, G is a map from E0 to M, yes? So in principle, G should act on any vector from P0. Yes?
Where EIJ lives?
EIJ lives in the J's copy of P of I. Yes?
Well, left-hand side lives in what? In M.
Yes.
And right-hand side does not.
No, the problem is that it's not clear what is this, yes? So you can't act by M on E, correct? So there is no way how to act by MC on EIJ, right? So how should I correct the formula? What should be on the right?
MEJ instead of P.
Absolutely. Yeah. Like this, right? So now this is fine, and this is the formula. And in principle, indeed, so if the two operators, well, by some chance, by some reason, the MC applied to MIJ and MC applied to MIJ prime, they coincide, and of course, the left-hand side also produce a kernel. But do you have any other suggestions? So do we have some other elements from the kernel, kind of independent on what is happening on the right in M? So some, of course, they do depend, but I mean, how to say, more some other elements in the kernel.
I thought all paths or length more than 0 will be mapped to vectors which which are dependent with images of like paths of length 0. Don't know if okay, maybe I'm a bit incorrect in my speech.
Well, I do understand what you are saying, and that's right. But let us even do a bit less kind of. So you are right, but let us do the step by step. So I mean, suppose we have some path, yes, some path C, starting at some S of C and terminating at T of C. And well, suppose we have one more arrow, say alpha, starting at S of alpha. So roughly speaking, we have a short path and we have a long path. And then this formula, I mean, this one, can be used for both short path and the long path, right? But the right-hand side would coincide for both. Yes, so I mean, we'll say this in a minute in more concrete way, but just for you to have an idea that you kind of this this formula can be applied to composition of a path and an arrow, and then this would give us some relations, and this is how we construct the resolution. So let's work it out in more details. So let us define P1. Yes, so recall that we are looking for the resolution 0 to P1 to P0 to M. So by definition, P1 is the direct sum now over alpha. So remember that P0 was defined as a direct sum over the vertices. And here, this is a direct sum over the arrows. And we take the dimension of the vector space corresponding to the starting point of alpha. And we take the projective P corresponding to the terminal point of alpha. Okay. Well, that's it. I mean, this is the whole thing, but we now have, let us define, so we define P1 and we need a map from P1 to P0. Yes, and so this is the map F. So in order to define it, again, let us fix a basis. So basis of P1. How does it look like? So we have B alpha J, where maybe I should write it. So J goes from 1 up to ds of alpha. So alpha is in P1 as usual. And B alpha is a path such that the starting point of, maybe I should move it, sorry. Oops. So B alpha is a path such that the starting point of P alpha, of B alpha, is the terminal point of alpha. So first of all, let me ask you, do you agree that this is indeed the basis of P1? So please raise your hand if you agree that this is the basis of P1. Okay, one hand. Okay, Dima agrees. What about other people? Okay, Xinyu also agrees. So Xinyu, can you explain why this is a basis? Just a few words.
P1 is the direct sum of PT alpha. The PT alpha is has the basis of the path going out of the vertex T alpha.
Right, right.
So it is just the SB alpha set.
Absolutely, absolutely, right. So just coming from the definition, and so this is the basis, and now we have to define. So we want to define f of B alpha. So any suggestions? Okay, maybe let me write down the formula and then we will stare at it and then try to understand whether it makes sense. So what do I do first? So I take the B alpha J. So this is a path starting at the terminal point of alpha. And then I take the composition with alpha. Okay, so what is this? This is a path which somehow starts at the starting point of alpha, okay, and terminates at the same place where B alpha does. So let me take this in brackets and put the J here. So I want to say that this guy can be understood as an element of P0. So can somebody explain how and why? So recall that J here is an element from 1 to D of S of alpha. So Andrei, is it kind of clear why this is an element from P0?
Sorry, I still don't understand why we have such a basis for P1.
Okay, so let's get back there. Yeah.
We have some DS alpha paths which starts at T of alpha, but we know that bases in P of T of alpha are all paths which starts there.
Yes, yes.
So
And
if you take any if you take any path, it's I don't understand. Okay, let D of S alpha be 1.
Absolutely.
Then
Yes.
we have what one-dimensional space P of T of alpha.
Well, it's not one-dimensional. You mean one copy of P of T of alpha? Yes.
Yes, one copy, but we say that the basis in this one copy is just one vector, or what?
So
I don't
the basis
understand.
in this one copy consists of all paths starting at the terminal point of alpha. So we take all paths which start at this T of alpha, and they form a basis. Yes, we know that P of T of alpha has a basis consisting of all paths starting at T of alpha, right?
Yes, right. But here we write, okay, here we
Yes.
but how many B we have for in our case?
Well, I mean, we don't know how many paths there are.
Yes, I understand. But here we write what? We write B, G alpha. Alpha is fixed, as I
Yes.
can see. And
Yes.
G, if we have just one copy P of T of alpha, have one value.
Absolutely.
So
Yes.
we have one element in basis.
No, because
Why?
if we take all paths, yes, so B alpha is a path. Yes.
Okay.
So let me write here.
Okay,
B alpha,
okay.
any path satisfying this property. So
Okay,
of course there are many. Yes.
then it's true. Okay, I understand.
Now let's get back to the next line. So once again, I want to consider alpha B alpha J as an element in P0. Is it fine? So Igor, does this make sense for you?
Yes, P0 was defined as a direct sum of P i's. So and P i's contains paths from I.
Right, right.
So
This I,
but the
yeah.
alpha contained in P of S alpha.
Right. So this is clear, but well, of course, this can't be the end of the definition because we don't have any relation to M. Yes, we want to construct the resolution of M. Therefore, of course, the definition of F has to depend on M. So there is no choice. Yes, so otherwise we can't expect anything. So how can we incorporate this dependence? So let us write the following formula. So we have M alpha. So remember, this is the map corresponding to the map, to the arrow alpha. And then to this, we can apply this M alpha to an element M, J as a follows. Yeah, so remember this M J S of alpha sits in M S of alpha. And this is actually one of the basis elements we fixed so far. And well, we can apply to this basis element our operator M alpha. Okay, so well, can you tell me where the result belongs to?
It's MT of alpha.
Absolutely. So we know that in MT of alpha, we have a basis M, well, I need some letter L, T of alpha. This is a basis, therefore any element can be decomposed as a direct sum of these elements with some coefficients. Let me denote this by L. L from 1 to G T of alpha. Okay. So these are just some elements. And then, so I want the formula to be dependent, and I write this as minus the sum L from 1 to G T of alpha. And I put here the same coefficients, theta L. And so what else can I do? So do you have any suggestions? So here I have some dependence on L, but what can I put here to make it an element of P0? Okay, maybe I write it and you will let me know if this makes sense. So I take my path B alpha, which is given for me, and then I put this L upstairs.
Maybe we should change M to B somehow.
Say it again.
Okay.
Where?
You did this. Okay.
So does this formula make sense? So far, just on the level of notation. So is it clear what's written here? Or some questions or whatever? So it's fine, right? So of course there's no point. So let's see what do we need to prove. So we need to prove two things. Several things. So first of all, we need to prove that f is an embedding from P1 to P0. Second, we need to show that the image of f belongs to the kernel of G.
Sorry, in this formula,
Yes.
I bit missed. We have alpha, we checked on B alpha, then we.
Well, it's not X on B alpha, but we have rather concatenation. Yes. So.
Okay.
So alpha B alpha is the path starting at S of alpha and terminating at T of B alpha.
Okay. Okay, and B alpha is path which is starting in T of alpha.
Absolutely.
So then we should in the second command probably we should have. Okay, maybe. Sorry, it starts at the same point or in different.
So you mean B alpha and alpha B alpha, or
yes,
or
yes.
They start at different points, but they terminate at the same point.
Okay, and
so you see, f should be a homomorphism of representations. Yes, so this means that we have to map each vector space of. So we have to, maybe I write it somewhere. Just as a comment. So we need to map f, I don't know, some letter. Oh, what letter do we have? So say A. So this should be mapped from P1A to P0A, right? For all A. And so therefore the if we take B alpha J, so this belongs to P1 T of B alpha. So do you agree?
yes, probably.
So therefore, an important thing is that we need to have the same terminal point. But these guys, they have different starting points, but the same terminal points, and it's fine. Okay?
Okay.
So, well, we have to show that the image of f belongs to the kernel of f, and finally, we have to show that they are equal. Okay. So, so just because we are proving that the so this would prove that the sequence uh, 0 to P1 to P0 to M to 0 is exact. So since we've already shown that P0 to M is a surjection. Okay. So Okay, so we have no time now. Okay, so just let us start with these formulas next time, and we'll complete the theorem. So any questions, comments, remarks?
I don't know if it will be okay. Can you put some notes to the site?
Absolutely, I will do this.
Okay. I mean, what you write here on
I do
the
understand.
lecture. Okay.
Yeah. So
Okay,
I had them
thank
on my computer. I'll upload them to the web page so you can find this there. So the proof to be completed next time. So further questions? So okay, if not, I'll save the notes and I stop sharing. So then see you next week, and then I'll, as usual, upload the homeworks, and so please send me the solutions again as usual. See you next week.